Modern offshore wind turbines are some of the largest rotating machines ever built. An 8-megawatt turbine features a rotor diameter spanning nearly 2 football fields, intercepting massive amounts of kinetic energy in highly turbulent, corrosive marine environments. The industry started in 1990 with a single 220-kilowatt prototype installed in shallow Swedish waters. Today, utility-scale arrays deploy hundreds of megawatts across dozens of square kilometers of open ocean. Building these remote arrays requires specialized heavy-lift vessels, subsea cabling, and complex maintenance logistics. The baseline capital required to build and operate here dwarfs terrestrial wind projects. The engineering of these structures is ultimately a brutal techno-economic balancing act, where physical possibility is constantly weighed against financial viability. The framework of that model is the levelized cost of energy, or LCOE, determining viability over a 25-year lifespan. The numerator groups all money spent, capital investment plus operations and maintenance. The denominator represents the total electricity generated, the physical energy yield. The entire trajectory of offshore wind development comes down to managing this specific fraction. Developers willingly take on the massive financial burden of the numerator because the ocean allows them to aggressively expand the denominator. This chart maps out the typical capital expenditure for an offshore wind farm. You'll notice that the turbine machinery itself constitutes roughly 44% of the initial upfront cost. That baseline cost is a direct result of the environment. The nacelle and blades must be engineered to withstand constant bombardment by saltwater, extreme aerodynamic shear forces, and continuous mechanical fatigue. Then there is the cost of the substructure. In water depths up to 60 meters, developers typically rely on bottom-fixed foundations. This involves driving a massive steel cylinder, called a monopile, directly into the seabed to anchor the tower. But the most favorable shallow water sites close to shore are becoming saturated. To find the space necessary for new utility-scale projects, developers are being forced out into deeper open ocean environments. When the water is too deep for a steel monopile, the engineering shifts to floating architectures. These systems use submerged buoyant bases tethered to the ocean floor with heavy mooring lines to maintain dynamic stability. While floating platforms unlock vast new territories for energy capture, they require complex mooring hardware and highly specialized installation procedures, driving the capital costs in our LCOE numerator even higher. To understand why investors agree to fund these deep-water floating arrays, we have to look back at our equation and focus on the denominator, the energy generation. Over the open ocean, there are no mountains, trees, or cities to create surface friction. Wind speeds are consistently higher, less turbulent, and much more predictable than they are over land. We measure this using the capacity factor. Onshore projects average a 27% capacity factor, while offshore pushes to 45%. Converting percentages to raw metrics, standard onshore yields 2,365 full load hours, whereas offshore targets 4,000 hours. By nearly doubling the energy output of each turbine, the denominator scales up aggressively enough to absorb the inflated capital and maintenance costs required to operate at sea. We can see this relationship clearly by simplifying the original LCOE model. This derived equation groups the costs and divides them directly by the full load hours. Here, full load hours is the critical variable. As operating hours increase, final energy costs drop exponentially. Capturing the kinetic energy at the rotor is only the first step. Inside the wind farm, turbines are linked together by an internal electrical grid, typically operating on alternating current at 33 or 66 kilovolts. As power travels through these subsea cables toward the central offshore substation, electrical resistance naturally converts a portion of that generated electricity into heat, resulting in line losses. Any energy burned off as heat before it reaches the substation is energy that cannot be sold. It directly subtracts from the total full load hours, driving the final LCOE back up and threatening the project's financial margin. Once the power is collected at the offshore substation, the final engineering hurdle is transmitting hundreds of megawatts across the seabed to the terrestrial grid. For farms located close to land, high-voltage alternating current, or HVAC, is the standard transmission method. But as cables extend past 100 kilometers, alternating current begins to suffer severe capacity losses due to cable capacitance. If developers try to push alternating current over extreme distances, the resulting line losses strip away a massive portion of the denominator, effectively negating the offshore wind advantage. This illustrates the alternative. Routing power through an offshore converter station using high-voltage direct current, or HVDC, allows energy to travel hundreds of kilometers with near-zero loss. However, building these massive converter stations requires highly specialized power electronics, severely driving up capital investment. The decision between the two systems is a strict mathematical tipping point. Engineers will only accept the immense capital cost of an HVDC converter when the distance to shore makes the preserved energy yield more valuable than the initial hardware investment. This continuous balancing of the LCOE fraction is exactly what has dictated the industry's behavior over the last decade. This line chart tracks the levelized cost of offshore wind from 2010 to 2015. As developers optimized arrays and supply chains, the cost dropped sharply. Projecting forward, recent European auctions dipped below €50 per megawatt-hour, bringing offshore wind into direct parity with fossil fuels. That price compression is the result of attacking both sides of the equation simultaneously. Mature manufacturing and logistics are pulling the capital costs down, while increasingly massive rotor diameters push the energy yield higher. The initial investments of the 1990s carried enormous technical and financial risk, but decades of iteration have mathematically and commercially validated the model. Now, the industry is preparing to scale the next generation of hardware. Fleets of 8-megawatt turbines mounted on floating architectures in the deep ocean. These multi-thousand-ton steel structures are positioned far out at sea for a single purpose: to intercept undisturbed high-velocity wind and maximize the energy generation denominator. As HVDC transmission systems become more cost-effective and floating substructures reach serial production, the offshore potential becomes nearly limitless. The modern utility-scale offshore wind farm is the physical manifestation of this mathematical optimization, a 25-year gamble against the ocean, calculated to the last kilowatt.